As of now, Earth remains the only confirmed location in the entire universe where life is known to exist. Every organism, every ecosystem, and every civilization that has ever emerged has done so on this single planet. Despite decades of exploration and technological progress, no direct evidence of life has yet been found beyond our world. Mars, Venus, Europa, Titan, and countless other bodies have been studied closely, but the universe has not yet revealed another living home. Still, this conclusion feels incomplete. When we step back and consider the sheer scale of the cosmos, the idea that life exists only here becomes increasingly difficult to accept. The observable universe contains hundreds of billions of galaxies, each with billions of stars. Around many of those stars orbit planets of every size and type imaginable. Rocky worlds, ocean worlds, frozen worlds, and planets orbiting calmly in regions where temperatures could allow liquid water to exist. Earth itself is not a perfect place for life. Throughout its history, it has been shaped by destruction as much as creation. Massive asteroid impacts have wiped out entire species. Ice ages have locked the planet in frozen silence. Volcanic eruptions have altered the atmosphere and oceans. And yet life survived. It adapted, diversified, and became increasingly complex. If life could emerge and persist under such unstable conditions, then it raises an important question. What might be possible on planets that are even more stable than Earth? This question has led scientists to explore the idea that Earth may not be the most habitable world in the universe. In fact, there could be planets that are larger, longer lasting, and better suited for life than our own. These are sometimes described as super-habitable worlds. They are not barren deserts like Mars, nor hostile pressure cookers like Venus. Instead, they are planets where life might have an easier time starting, surviving, and evolving over extremely long periods of time. Among the many exoplanets discovered so far, one of the most compelling candidates for such a world is known as KOI 5715.01. While the name sounds technical and distant, the planet itself represents one of the most intriguing environments scientists have ever identified. It is a large, rocky planet, approximately twice the size of Earth. Located comfortably within the habitable zone of its star, being in the habitable zone means that temperatures on the surface could allow liquid water to exist. Water, as far as we know, is essential for life. On Earth, it acts as a solvent for chemical reactions, a medium for transporting nutrients, and a stabilizer for climate. A planet with long-term access to liquid water immediately becomes a serious candidate for habitability. The size of KOI 571501 adds another layer of intrigue. A planet twice the size of Earth would offer vastly more surface area. Continents could stretch across enormous distances. Oceans could be deeper and more expansive. With more land and water available, ecosystems would have room to grow, diversify, and interact in ways that may not be possible on smaller worlds. Imagining such a planet challenges our sense of scale. Traveling between distant regions might take days or even weeks. Entire species could evolve in isolation, separated by vast distances, leading to extraordinary biological diversity. Life would not be constrained by limited space, and evolution could explore countless pathways simultaneously. What truly sets KOI 5715.01 apart, however, is not just the planet itself, but the star it orbits. Our sun is classified as a G-type star, often referred to as a yellow dwarf. Stars like the sun are relatively stable, but they have a finite lifespan of about 10 billion years. Earth is already nearly halfway through that timeline. In roughly 5 billion years, the sun will expand into a red giant, dramatically altering or potentially destroying the inner planets. KOI 5715.01 does not orbit a star like our sun. Instead, it circles an orange dwarf star. These stars are slightly smaller and cooler than the sun, but they possess a remarkable advantage: longevity. Orange dwarf stars can remain stable for tens of billions of years, sometimes lasting up to 70 billion years. This extended lifespan changes everything. Life on Earth has had approximately 4 billion years to evolve. On a planet orbiting an orange dwarf star, life could have 10 times that amount of time or more. Evolution would not be rushed. Complex organisms could emerge slowly and steadily. Intelligence might have time to develop multiple times, refine itself, and potentially reach levels far beyond our own. With such immense timescales, it is not difficult to imagine civilizations advancing far beyond humanity's current understanding of technology. Energy sources we consider futuristic today might be commonplace there. Entire planetary systems could be engineered for stability and efficiency. The boundaries between biology and technology might blur entirely. Despite all of this potential, there is one major limitation that places KOI 5715.01 firmly in the realm of imagination rather than exploration. Distance. The planet lies approximately 3,000 light-years away from Earth, even at speeds far beyond anything humanity can currently achieve. Reaching such a world would take tens of thousands of years. For now, KOI 5715.01 exists as a reminder of what the universe is capable of creating. It represents possibility rather than destination. It shows that planets better suited for life than Earth may exist, even if they are currently beyond our reach. Because of this limitation, scientists have also focused their attention on worlds much closer to home. And among these nearby discoveries, few have generated as much excitement as a small, unassuming star located just 39 light-years away. Orbiting this star is the TRAPPIST-1 system, a compact collection of 7 Earth-sized planets packed tightly together. 3 of these planets orbit within the star's habitable zone, making them strong candidates for hosting liquid water and potentially life. The TRAPPIST-1 system was first identified in 2017, and it immediately became one of the most studied planetary systems ever discovered. Astronomers detected these planets by observing tiny dips in the star's brightness as each planet passed in front of it. This technique, known as the transit method, allowed scientists to determine the planet's sizes, orbits, and approximate compositions. One of the most fascinating aspects of TRAPPIST-1 is the age of the system. It is significantly older than our own solar system. This means that if life formed there, it could have had billions of extra years to evolve before life on Earth had even fully emerged. Among the 7 planets, TRAPPIST-1e stands out as particularly promising. It is slightly smaller than Earth and appears to receive just the right amount of energy from its star to allow water to exist on its surface. Some models even suggest that it could possess a dense atmosphere, potentially rich in oxygen. Such conditions could make TRAPPIST-1e more favorable for life than Earth itself. However, the system also presents challenges. The star is a red dwarf, much cooler and smaller than the Sun, to receive enough warmth. The planets must orbit extremely close to it. This close proximity likely causes tidal locking, where one side of each planet always faces the star, while the other remains in darkness. As a result, one hemisphere could be intensely heated while the opposite side remains frozen. Under the right conditions, a narrow region between these extremes could provide a stable environment where life might exist. Even with these challenges, the TRAPPIST-1 system represents one of the closest and most realistic opportunities for discovering life beyond Earth. Living in a system like TRAPPIST-1 would feel fundamentally different from anything experienced on Earth. The sky itself would constantly remind its inhabitants that they are not alone in their system. Neighboring planets would appear large and bright, clearly visible without telescopes, slowly moving across the sky. These worlds would not be distant points of light, but massive disks with visible colors, shadows, and perhaps even atmospheric patterns. The closeness of the planets could have profound effects on life. Gravitational interactions might produce stronger tides, influencing oceans and possibly even geological activity. These forces could help recycle nutrients and energy, creating dynamic environments where life has many opportunities to adapt and evolve. Over long periods of time, such conditions might drive rapid diversification, producing ecosystems unlike anything found on Earth. If life did emerge on TRAPPIST-1e or its neighboring planets, it would likely have adapted to extreme contrasts. One side of the planet would face constant daylight, while the other would remain locked in eternal night. In between these extremes lies a narrow region where temperatures could remain relatively stable. This twilight zone could stretch endlessly around the planet, forming a continuous band where life concentrates. Civilizations, if they developed there, might build their entire societies within this strip. Cities could extend in a ring around the planet, always positioned at the balance point between heat and cold. Agriculture, architecture, and daily life would be shaped by this unique geometry. Seasons might not be defined by axial tilt as they are on Earth, but by subtle variations in stellar activity and atmospheric circulation. Despite these fascinating possibilities, red dwarf stars introduce uncertainties. In their early stages, they are known to produce powerful flares capable of stripping atmospheres and bombarding planetary surfaces with radiation. Whether the TRAPPIST-1 planets managed to retain thick atmospheres long enough for life to gain a foothold is still under investigation. Some models suggest magnetic fields or dense atmospheres could provide sufficient protection, while others paint a more hostile picture. Even so, the TRAPPIST-1 system remains one of the most promising nearby laboratories for studying habitability. Its proximity makes it an ideal target for future telescopes designed to analyze planetary atmospheres in detail. If signs of water, vapor, oxygen, or other life-related gases are detected, it would represent a breakthrough moment in human history. While TRAPPIST-1 challenges our understanding of planetary systems, another world presents a more familiar, yet equally intriguing case. Kepler 452b has often been described as Earth-like, but that description only tells part of the story. In reality, it is both similar to Earth and fundamentally different, in ways that could significantly influence life. Kepler 452b orbits a star very similar to our Sun, completing one orbit every 384 days. This creates a year only slightly longer than Earth's, suggesting that seasonal cycles, if they exist, could feel familiar. The amount of energy it receives from its star places it comfortably within the habitable zone, at least for now. However, Kepler 452b is larger and more massive than Earth. Its increased mass would result in stronger gravity, altering how life interacts with its environment. Movement would require more energy. Flying organisms might be rare or non-existent. Plants could grow shorter and sturdier, while animals might evolve compact, muscular bodies designed to cope with the stronger pull. At the same time, this higher gravity could help the planet retain a thick atmosphere. A dense atmosphere would provide better insulation, reducing temperature extremes between day and night. It could also offer greater protection from cosmic radiation, creating a more stable surface environment for life to develop over long periods. One of the most unusual aspects of Kepler 452b is the apparent absence of other large planets in its system. Unlike our solar system, which contains massive gas giants like Jupiter, Kepler 452b seems to orbit its star alone. For a long time, scientists believed gas giants were essential for protecting inner planets from asteroid impacts. More recent studies, however, suggest the situation is more complex. In some cases, gas giants can redirect asteroids toward inner planets rather than away from them. Without a Jupiter-like planet, Kepler 452b might experience fewer catastrophic impacts, allowing life to evolve with fewer interruptions over billions of years. Despite these advantages, Kepler 452b faces a serious long-term threat. Its star is older than our Sun, and as Sun-like stars age, they gradually become brighter. This increase in energy could push the planet toward a runaway greenhouse effect. Oceans could begin to evaporate. Temperatures could rise uncontrollably, and the planet might eventually resemble Venus rather than Earth. If this process is already underway, Kepler 452b may currently exist in a narrow window where life is still possible, but time is limited. Life there would need to adapt quickly or face extinction as conditions slowly deteriorate. This highlights a critical truth about habitability. it is not permanent. Even planets that seem perfect can change dramatically over time. As scientists consider these possibilities, attention naturally turns to worlds that challenge our assumptions even further. Not all habitable planets need continents, forests, or familiar landscapes. Some may be dominated entirely by water. Kepler-22b is one such world. Located roughly 600 light-years away, it orbits within the habitable zone of its star and is puzzled astronomers since its discovery. The planet is larger than Earth, but its exact composition remains uncertain. Observations suggest it could be a water world, covered by a vast global ocean with no exposed land. If this is true, Kepler-22b would represent a radically different type of habitable environment. Instead of continents and shallow seas, it would feature an endless ocean stretching across the entire planet. Beneath the surface, immense pressure would shape the chemistry and physics of the environment in ways unfamiliar to us. Life in such an ocean might rely on energy sources other than sunlight. Deep beneath the surface, hydrothermal vents could provide heat and nutrients, supporting complex ecosystems as they do on Earth. Over time, life could adapt to these conditions, producing organisms with extraordinary forms and abilities. Intelligence, if it emerged in such an environment, might look very different from anything humans recognize. Without fire, metal, or dry land, technological development would follow entirely different paths. Communication, construction, and exploration would all be shaped by the surrounding water. For human explorers, visiting Kepler-22b would be an experience unlike any other. There would be no solid ground to stand on, no mountains to climb, no familiar horizons. Instead, the planet would present an endless expanse of water, hiding its secrets beneath layers of depth and pressure. These worlds, taken together, reveal a universe filled with diverse possibilities for life. They show that habitability is not a single formula, but a wide range of conditions under which life can emerge and persist. Some planets may favor slow, stable evolution over immense timescales. Others may offer brief windows of opportunity where life must adapt quickly or disappear. Beyond these well-known candidates, scientists have begun to consider worlds that challenge the very definition of habitability. Not every planet needs to resemble Earth on the surface to support life. Some may rely on entirely different mechanisms to remain warm and active. One such example is Proxima Centauri b, the closest known exoplanet to our solar system. Orbiting within the habitable zone of Proxima Centauri, a red dwarf star just over 4 light-years away, this planet has become one of the most intensely studied worlds beyond our system. Its proximity makes it a prime target for future exploration and atmospheric analysis. Proxima Centauri b likely experiences conditions similar to the TRAPPIST-1 planets. It is probably tidally locked, with one side perpetually facing its star and the other in darkness. Yet even under these constraints, climate models suggest that a thick atmosphere or large oceans could redistribute heat efficiently, enough to prevent the planet from freezing or overheating entirely. If oceans exist on Proxima Centauri b, they could act as massive heat reservoirs, absorbing energy on the day side and releasing it on the night side. Winds and currents might create a relatively stable environment in the twilight zone, where temperatures remain suitable for liquid water. Life, if present, would most likely concentrate in these regions, evolving under conditions of constant but moderate illumination. However, Proxima Centauri itself poses a significant challenge. As an active red dwarf, it produces frequent stellar flares that could expose the planet to intense radiation. Whether Proxima Centauri b has retained a protective atmosphere or a magnetic field strong enough to shield its surface remains uncertain. The answer to this question could determine whether the planet is truly habitable or merely Earth-like in appearance. Moving farther out into the galaxy, scientists have also identified planets that may be habitable beneath thick layers of ice. These icy worlds, often referred to as subsurface ocean planets, may not receive enough sunlight to maintain liquid water on the surface. Instead, Internal heat generated by tidal forces or radioactive decay could keep vast oceans liquid beneath frozen shells. In our own solar system, moons like Europa and Enceladus provide compelling examples of this phenomenon. If similar worlds exist around other stars, they could vastly expand the number of potentially habitable environments in the universe. Life in such oceans would be completely isolated from the surface, evolving in darkness around sources of geothermal energy. On these planets, ecosystems might develop around underwater vents, powered by chemical reactions rather than sunlight. Over time, complex food webs could emerge, sustained entirely by internal planetary processes. This suggests that life may be far more resilient and adaptable than previously thought. As the search for habitable planets continues, scientists are also refining the tools used to detect signs of life. Rather than focusing solely on Earth-like conditions, researchers are now looking for biosignatures that could indicate biological activity. Under a wide range of environments, gases such as oxygen, methane, and even more complex molecules could serve as clues. Depending on the planetary context, future space telescopes are expected to analyze the atmospheres of nearby exoplanets with unprecedented precision. By studying how starlight interacts with atmospheric gases, scientists hope to identify chemical imbalances that cannot be easily explained by non-biological processes. Such discoveries would represent one of the most profound moments in human history. Yet even if life is detected elsewhere, many questions will remain. Will it be simple microbial life or something more complex? Will it share a common origin with life on Earth or arise from entirely different chemical pathways? Each possibility carries profound implications for our understanding of biology and the universe. These discoveries would also force humanity to confront its place in the cosmos. For centuries, humans have wondered whether Earth is unique or simply one example among many. The growing list of potentially habitable planets suggests that the conditions for life may not be rare, but rather a natural outcome of evolution. At the same time, the vast distances between stars present a sobering reality. Even the closest potentially habitable planets are many light years away. Far beyond the reach of current human technology, any contact with life beyond Earth, if it occurs at all, is likely to be indirect, mediated through telescopes and data rather than physical exploration. Still, the act of searching itself carries immense value. Each new discovery expands our understanding of planetary systems and challenges. Assumptions formed from studying only our own solar system, the diversity of worlds, now known, suggest that nature is far more creative than once imagined. In this broader context, Earth takes on new significance. It is not merely our home, but a reference point against which all other habitable worlds are measured. Studying exoplanets helps us understand the delicate balance that makes life possible here, and how easily that balance can be disrupted. Ultimately, the search for planets is also a search for perspective. It reminds us that life, wherever it exists, is shaped by its environment in profound ways. Whether on a tidally locked world around a red dwarf, a water-covered planet orbiting a distant star, or an icy moon with a hidden ocean, life adapts, persists, and evolves. As technology advances and our knowledge deepens, the question may shift from whether life exists elsewhere to how common it truly is. Each planet discovered adds another piece to this cosmic puzzle, bringing us closer to understanding place in an immense and mysterious universe